Okay, let's compare some strong acids to weak acids. And I really want to get into their chemical structure, their position on the periodic table, and what makes something weak versus strong based on its chemical structure. Okay, so here you can see is our list of strong acids. I do want you to know this list, okay? So hydrobromic, hydrochloric, hydroiodic, nitric, perchloric, and sulfuric acid all are strong acids, okay? So I want you to also know this list of weak acids: acetic, formic, hydrofluoric, hypochlorous, and nitrous, okay? These, I want you to know these things so that you can quickly recall what's a strong acid and what's a weak acid. So now, first of all, let's talk about the first three strong acids on this list: HBr, HCl, HI. And check it out. Here they are on the table. There's iodine, bromine, and chlorine. And if you remember the electronegativity trend, right? Electronegativity increases as we go up and to the right. And electronegativity is the ability of an element to attract electrons to itself. So if I compare iodine, bromine, chlorine, and fluorine to each other, fluorine is the most electronegative. But you can see that fluorine is a weak acid. So why is it that HF is a weak acid, but HBr, HCl, and HI are strong acids? Well, it's all about its dissociation into hydrogen, okay? So for example, this HF bond, so I'll write strong bond. That's a really strong bond because fluorine is so electronegative. So it doesn't want to dissociate because of how strong that bond is, okay? And HBr, HCl, HI, those are fairly okay in their bond strength. However, those bond strengths are weak enough that when you put these in water, they completely dissociate, okay? So that's one factor that we can say. Another factor that's similarly related is also about how the anion, right? So we remember all of these are HA, where it becomes H plus and then A minus. So then now for some of these more complicated ones, it's really all about how the anion can attract electrons to itself and make that bond right there strong. So I'm going to point out all of those bonds to hydrogen, and we'll note that those are all strong bonds for the weak acids. So I realize that sounds backwards, right? But they are weak acids. In other words, they don't want to dissociate because that bond is strong. On all of our strong acids, so I'll draw this like with maybe a different color. Where's my red? So sure, we'll say blue. Oh, there we go. I got red. Okay. So now all of these bonds right here, these are all weak bonds. Okay. Or I should say relatively weak bonds, because these acids are known to dissociate completely. So that means those bonds have to break. Okay, so now what is it about the structure of some of those acids that make those bonds strong? Okay, so here's another example problem that I want you to think about. So pause the video if you have to. So determine the oxidation number of chlorine for each of the following acids, and can you discern a relationship between acid strength and oxidation number on the central atom? So here I'll say ox just for the oxidation number of chlorine. And so for HClO, so I'll just do a quick example right here. We know that it all has to add up to 0. We know that the hydrogen is +1. The oxygen is always -2. And then now we want to figure out what the chlorine is. Most of the time chlorine is -1, but when chlorine is a central atom, it is not -1. Okay, so now if you think about this math here, that means this chlorine has to be a +1 oxidation state. So +1, okay? And if you're good at your math and your pattern recognition, then you'll see now with these formulas, all we're doing is adding an extra oxygen atom. And because each oxygen atom is -2, that means the oxidation state of chlorine has to increase by +2 for each oxygen that we add. And if you don't see that right away, that's okay. Go through this formula and add up the numbers for yourself. Oops, you know what? I made another column, but look, I had a column right there. Some of you were probably like, what is he doing? Okay, so right, here we go. So that's +1. So now that means when I add each extra oxygen, the oxidation state of chlorine increases by +2. So +3 for chlorous acid, +5 for chloric acid, and +7 for perchloric acid. And now you will notice that perchloric acid is a strong acid, but all these other acids are considered weak acids. And so, right, the hypochlorous, there it is, that's on that list. But you can also see that not only is hypochlorous a weak acid, but chlorous acid and chloric acid are also weak acids. So what is happening with that oxidation state, and what is it that make these things weak? Well, this arrow right here, this blue arrow, that's trying to show you, all right, the electron density in this chemical bond right here. So we remember that a chemical bond is made up of 2 electrons, okay? And so I'll also point out here that, oops, let me change colors. Let's see if I can do that. Give me the red color. Perfect. Okay. So this red is oxygen right here. Okay. The white atom right there, that's hydrogen. And then in these pictures, all of the green atoms are chlorine. So now, because this chlorine is +1, it's positively charged, right? It is pulling electrons away from this central atom, okay? And then also because there's only one of those chlorines, so the oxygen doesn't count right here because it's the same for each one of these structures. So what we're really interested in is this chunk of the molecule that I'll circle for all of these examples, right? Okay. So what we notice here is now, even though, so what's happening is electron density is being pulled away from this area. However, because this hypochlorous is only +1, not very much electron density is pulled away from that bond. So that makes that bond strong, which is why it does not want to dissociate. And you can see it's the weakest acid of all of them, meaning its oxygen-hydrogen bond is the strongest. So now let's look at chlorous, HClO2. So you can see now it's a +3 oxidation state, okay? And so that means this electron density is getting sucked out of this bond even more so. And you can see there's a huge increase in the Ka, which means this bond is more likely to break apart. Same chloric acid is +5, so that's even more electron density getting sucked out of that bond. And then finally, perchloric is a +7 oxidation state, so it really wants to suck electron density out of that bond. And that's why perchloric acid will dissociate completely, because that HO bond is incredibly weak. Okay, and then I know I described this already with HCl, HBr, and HF, but if we look at now, if we compare hypochlorous to hypobromous to hypoiodous, we're going to see the same trend that we saw with the electronegativity. Okay, so you can see here, we know that chlorine is more electronegative than bromine, is more electronegative than iodine. So we'll say number 1, so most electronegative, second most electronegative, third most electronegative. Okay? And you can actually see here the most electronegative element is pulling electrons out of that bond and correspondingly has, of these three, the largest Ka value. So recognize that all of these Ka values are incredibly small. So that means these are all weak. But you notice that hypoiodous is the weakest, and that's because the iodine is the least electronegative, meaning it doesn't pull electron density out of that bond very well. And because it can't pull that electron density out of that bond, this bond is the strongest, so the least likely to dissociate.